11.7 is on page 784, talks about strategy for testing series. So what we want to really put everything together. This is a review of 11.2 through 11.6. There are no sequences here, so 11.1 is excluded out of this. So they put a bunch of series in mixed order, and this is the best way for you to check how to use what. When I glance at number 2, and this is on page 786, the problems, when I look at problem number 2, I'm thinking, well, let's see. If I look at number 2, two options should come to my mind. Those are positive. Either think of the comparison test, or, for sure, n over n cubed, right? Which is 1 over n squared. That's a p series, right? And use limit comparison test. So limit comparison test works for sure. Try comparison test, it might be faster. I'm looking at number 4, and what's the first thing that comes to mind? Those are growing at the same rate. This diverge by test for divergence. Of course, I'm just telling you the outcome and what to use. Use test for divergence, you're going to get this limit not to equal 0, therefore it'll diverge. Number 6, if I'm looking at number 6, I noticed that, so by glancing at it, I noticed that those are raised to the n power. So I'm thinking of this as the series n equal 1 to infinity of n squared over 1 plus n cubed raised to the n power. So if I take the limit as n approaches infinity of the nth root of that, that would be the limit as n approaches infinity of n squared over 1 plus n cubed. And if I divide by the highest power term of the denominator, which is n cubed, each of those, I should get a 0. And you would get a conclusion by using the ratio test. It seems this is absolutely by the root test. It seems this is absolute conversion by the root test. On number 8, alternating series test seems to work, but you have to show that this is decreasing. A better way of doing this, since it is an exponential, use the ratio test, and that's guaranteed to give a result. When I look at this problem, this is really n squared over e to the n cubed. I could use the integral test for sure. Or, since it has an exponential in it, the ratio test would work as well. So when you look at a problem on the test, it's not, let me start working at it. It's think about it for a minute and say, okay, well, what should I use? Which test should I use? So when I look at number 12, I'm thinking of the comparison test. Get rid of the one, see how that works. And if not, for sure, 1 over k, the square root of k squared, which is 1 over k squared. This is a p series. Use the limit comparison test. That works for sure. So far so good. Number 14. Since I do have an exponential in there, I would say possibly the ratio test would do the trick. And if not, I could say in absolute value though, in absolute value, this is less than or equal. The biggest that could ever be is a 1, right? And I could show that this converge, and therefore that will converge, absolutely convergent by comparison test. And how can I show that this converge? I could use the limit comparison test. I could use the comparison test. I could use the integral test. I could use the ratio test. Any of those will do. And the reason you want to put an absolute value on it, because if you want to use the ratio test, it doesn't matter. But if you want to use the integral test, the comparison test, or even the limit comparison test, those have to be positive. Sine of 2n is not positive. By putting an absolute value on it, you're using 11.6 showing if the absolute value converge, the series is absolutely convergent. As you see, well, I'm aiming to do all the evens. Number 16. If I glance at that, well, automatically, the limit n approaches infinity equals 0. I'm thinking comparison test will do, probably. And if not, what dominates the top? The square root of n to the fourth, the denominator n cubed. Isn't that 1 over n? I know that diverge and limit comparison test. Make sure to state those and go from there. Number 18. Well, obviously, alternating series test, because this is decreasing. It's positive for n equal 2. And the limit equals 0, therefore converts by atomic series test. Done. 20. On 20, I could try the comparison test, but I know for sure the cube root of k over, that's k, the square root of k. That is k to the 1/3. So that's k to the 1/3. And this is k to the 3/2, right? Well, yeah. So if I really combine those, I'm looking at whatever that is, 1 over k to a power. This is a p series, right? And limit comparison test will do. Okay, on number 22, if I take 2 plus sine of k, the biggest this could ever be is 1. And the smallest that could ever be is negative 1. So I could say I could say 2 plus the sine of k is between 1 and 3. And if I put 1 over 1 is 1. Switch the inequality. So, if I take the limit as n approaches infinity of 1 over 2 plus the sine of k, wouldn't that be between 1 and 1/3 for sure? That 1/3 is not coming out. 1/3, which means it doesn't equal 0, therefore diverge by test for divergence. Right? This problem we've seen too many times by now. I'm not sure if you recall, if you take the limit as n approaches infinity, in L'Hopital we saw that. If you take the limit as n approaches infinity, isn't that infinity times 0? So you're going to rewrite this as what? You're going to rewrite this as sine of 1 over n over 1 over n. Remember the sine of beta over theta? And you're going to take the limit as n approaches infinity, because now you just made it 0 over 0 by L'Hopital. Isn't that the cosine of 1 over n times negative 1 over n squared over negative 1 over n squared? And as n approaches infinity, that approaches 0, and the cosine of 0 equal 1, which doesn't equal to 0, therefore diverge by test for divergence. Alright guys, how about 26? 26, since I see an exponential, I would use the ratio test. And if the ratio test gives you a hard time, split that up. This will be easier. Of course, that's not the only way to do the problem. You could say this converge, do R, geometric, do all of that, and use the ratio test on that piece alone. That'll work. 28. If I'm glancing at 28, I should be thinking, well, a couple of things. One, I could say this is less than or equal e to the 1 over n squared, right? Since that's the nth root of e. And take the e up front. P series comparison test will do, right? That's probably the easiest way to run this out. You could use the integral test as well, that works, but that's a lot longer. And if I look at this problem, number 30, well, alternating series test is the way to go, but you have to show that it's decreasing. So you have to take a derivative to show it's decreasing. And obviously, number 32, we are going to use the ratio test. I could use the root test first, the limit as n approaches infinity, because that's raised to the n. The nth root of that would be the limit as n approaches infinity of n factorial over n to the fourth, right? And now when you look at this, you're thinking, well, what can I do? I could use the ratio test on that. Now, we normally try not to use two tests, but you could, but just be careful with that, because there are some drawbacks. And if I look at number 34, a couple of things I could do. Whenever I see something like this, I could say, well, let's see. If I take n plus n cosine squared of n, since that's always positive, I know the biggest that could ever be is 1, which is 2n, true? And if I put 1 over, wouldn't that be bigger than 1 over 2n? Isn't that 1/2 the series of 1 over n? Doesn't that diverge p? Right? And smaller, therefore, by the comparison test, that diverge. And there's the homework.